Good afternoon, everyone. Welcome to General Chemistry Laboratory 111. I will be your TA this semester. My name is Yiting Liao. Yiting is my first name. Liao is my last name. And since this is your first time to come over here, I'd like you to copy down my contact information inside your contract book. So this is my email and this is my office hour. So if you have any question, you can directly email me or come to see me in my office hour. Okay. Today is your first time to over here, so we have several things to do today. So first thing is that I will introduce some background information about the experiment that you are going to do next week, and also I will show. And second, I will show you the surrounding of this lab. Okay, so right now I'm going to introduce the background of the experiment that you are going to do next week, and is in your contract book, chapter 4, the introduction of acid-base chemistry. So please open your book at chapter 4. So acid and base chemistry is the most fundamental, common, and general concept that you probably already learned when you are a senior high school student. And so first I will give you the definition, introduce the definition of acid and base, of acid and base. So actually the definition of acid and base evolved during the whole chemistry history. So in the very beginning, people differentiate acid and base substance by their taste. So the acid substance, the taste of acid substance is sour, and the base substance is taste bitter. So in the very beginning, people differentiate this acid and base by taste. And then the irony is these scientists develop a more scientific and more specific definition for acid and base substance. So what's one? It defined that acid substance can donate is the substance what can donate proton, and base is the substance what can donate hydroxide ion in aqueous solution. And after that, the Bronsted and Rory, these two scientists, they develop a more broader definition for differentiate acid and base. So acid is a substance what can donate proton, same as Arrhenius definition. But base is a substance what can accept proton. So after this, Lewis developed the Lewis acid base theory tells us, and this theory is the broadest theory so far, and it defined that the acid substance is what can donate electron, and base is what can accept electron. Okay, so far you know the definition of acid and base, so you know how to differentiate acid and base, and you already know there are many acidic substances and basic substances in our surrounding, and you use every day. Like the soap is a basic substance that you use in your bathroom, and the lemonade is acidic substance that you drink, you bought from Starbucks. So I need you to learn to know some common acids and bases that we use a lot in the laboratory, and you are going to use next week. And so I'd like you to know how to write the chemical formula of these common acid and base. And also know the name of this common acid and base. So the common acid and base that we are going to use next week is hydrogen chloride and sulfuric acid, H2SO4, and phosphoric acid, H3PO4. And the other three common bases that you are going to use next week is sodium hydroxide, NaOH, ammonia, NH3, and potassium hydroxide, KOH. So I'd like you to spend some time to memorize how to write down the chemical formula for this common acid and base, because you are going to write a lot next week. And if you memorize beforehand, then you can save yourself a lot of time in the lab next week. Okay, so after that, and one more thing that you have to do after you leave before you come next week is that you have to know how to write down the ionic equation and net ionic equation. And I know that all of you already learned this from the General Chemistry 110. And so I'd like you to go back to refresh your memory and know how to write down these two equations. Okay, so I don't want to spend much time on this, and because this is quite simple and you already learned about this from the General Chemistry lecture. So what you have to do is go back to refresh your memory and read carefully all the content in chapter 4 in your ChemTrack book. Okay? So please remember this. So the next thing, the most important part that you are going to do for the experiment, that you're going to do next week is that you are going to do the indicator-based acid-base titration. So what is that? The principle behind this indicator-based acid-base titration is that this method is nothing but the neutralization reaction between acid and base. So the net ionic equation for this acid-base titration is just like one proton can react with one hydroxide ion and become a water molecule. So what's the consequence for this acid-base neutralization reaction? First is that the number of the proton and hydroxide ion in the solution change. Second is the pH value change. Third is that this reaction accompanied by the release of heat. So what's the purpose that we are going to we need to use acid-base titration? This is used to define the concentration of an unknown solution. So the process is like that you have an unknown acidic solution, or you have an unknown concentration. You have an unknown acidic solution or basic solution, and then you use a standardized basic solution or acid solution to titrate this unknown sample. Then you can calculate the concentration for this unknown sample from the standardized solution. What is a standardized solution? Is a solution what its concentration is accurately determined by another method. So standardized solution is just a solution that you know is concentration accurately. So, but how do you know all the proton or hydroxide ion in your unknown sample is totally neutralized by the standardized solution? One of the approach is to use an indicator. Indicator is a chemical compound which can change its color according to the pH value of the solution. So you will observe the color change of your solution if you add your indicator into the solution when you reach the equivalent point, which is the number of the proton equal to the number of the hydroxide ion. Okay, so then you can use this equation to calculate the concentration of your unknown sample from the standardized solution. Right? I'm pretty sure you know this well. I just want to remind you, refresh your memory. And so for this indicator-based acid-based titration method, the thing that you have to keep in mind is that when you observe the color change, we assume we assume when you observe the color change, then we assume you reach the equivalent point. But in fact, it's not true, because when you observe this color change, we often call this endpoint. And endpoint is not equivalent point. So why? Because the indicator, the chemical itself, because of its nature, it changes color. The point it changes color may slightly away from the real equivalent point because of the nature of the compound. It's very hard to find a compound can change color exactly at the equivalent point like of your system. So this is a trade-off. We have to choose a right indicator which change color close to your equivalent point. So the most important thing for you to do this experiment is to choose the right indicator what can change the what can change color close to the equivalent point that you estimate. So simply to say is that at the point you have to choose indicator what has its endpoint approach to the equivalent point. So for here, this here is the titration curve, and the y-axis is the pH value, and the x-axis is the NaOH, a strong base, that standardized solution that you use to titrate your unknown acidic solution. And for this example is the strong acid and base titration. So in this case, the equivalent points will occur at pH 7. So in this case, phenolphthalein is the most best indicator that we can use for this strong acid-base titration. And this indicator phenolphthalein that you will going to use next week, the color change from pH 7 to pH 10. Sorry of this. It will form transparent color and turns to pink at pH 9 and become dark purple at pH 10. So the end point of this phenolphthalein is around pH 9. So it's slightly away from the equivalent points that we estimate. So in this case, you may slightly overestimate the concentration of your unknown sample, but it will not deviate. The difference will not is not super big. So because this indicator is kind of suitable for this strong acid-base titration. Okay, so you have to keep in mind is that first you have to choose the right indicator, and then you should know the endpoint is not the equivalent point. So you always slightly overestimate or underestimate the concentration of your unknown sample of your unknown sample when you are doing this indicator-based, acid-based titration. All right? Okay, so when you are performing this experiment, you have to build this setup first. You need a burette and you need a flask with your unknown sample in here in the flask, and then with your standard, and fill this burette with your standardized solution, and add 1 or 2 drops of indicator. Please don't add too much because this indicator is also is an acid or base, so it will affect the accuracy for your titration experiment. So only add 1 or 2 in your unknown sample is enough. And then you have to be careful. You have to titrate the standardized solution into your unknown sample very slowly and dropwise. And you have to shake and mix the solution after each addition. So then you can, and also put a white sheet under this flask, and then you can observe the color change very well. So be careful to do this step, and that will make sure you get an accurate, more accurate result. Okay, so keep in mind, titrate slowly and dropwise. Shake and stir the solution after each addition. All right, and then so after this, then you know what's the total value you add. What's the total value of standardized solution you add into your unknown sample, and then you can calculate the concentration of your unknown sample by using this formula that you already learned in general chemistry lecture. Here I just want to remind you how to do this. Then you can do it faster in your experiment. So the equation is that at the equivalent points. So again, keep in mind, we assume the endpoint is equal to equivalent point. So over here, we assume that at that point, the number of proton is equal to the number of the hydroxide. So the number of proton can use this formula to calculate is the concentration, which is molarity. The unit is molarity, and times value is equal to the so over here is the concentration of your unknown sample times the value of your unknown sample is equal to the concentration of your standardized solution times the value of the standardized solution, which is the total amount that you add from your burette into your flask. So then you can calculate. So then you can calculate the concentration of your unknown sample by is equal to the concentration of standardized solution times the value of standardized solution and over the value of your unknown sample. Okay, so here is the example. Here is a 10 millimeter. Here is the unknown sample, which is 10 milliliter HCl aqueous solution, and it's titrated by 0.1 molar sodium hydroxide, and the total added value of sodium hydroxide is 5 millimolar. So what is the concentration for this hydrogen chloride aqueous solution? So then you can use this formula. So the concentration of hydrogen chloride is equal to times the value 10 milliliter is equal to the concentration of sodium hydroxide 0.1 molar times the total value added 5 milliliter over here. So the concentration of hydrogen chloride is equal to the 0.05 molar. Okay, so this is the most important thing that you need to perform next week in the lab. So please refresh your memory about how to calculate the molarity and how to write down the net ionic equation, the ionic equation and net ionic equation, and to memorize those common acid-base chemical formulas. And okay, so get well prepared and read before you come to the lab next week. Okay, so and then I will show you the surrounding of our lab, and so and then you are free to go. I will see you next week. Have a good weekend. Bye bye.